But hang on, I actually don't mean becoming mathematicians to be. I mean mentoring mathematicians in the here and now. When we teach kids to write at younger grade levels, sometimes I'll hear teachers say, hey, fourth grade writers, let's write today. We're going to engage in the work of writing. We're going to do the things that writers do. We're going to write, and then I'll read and comment and reflect on your work. Could we engage students in the work of mathematizing? Could we ask them to mathematize at their grade level? Could we have 7th grade mathematicians or 10th grade mathematicians, kids mathematizing at an Algebra 1 level? I think we can, and I think the development, if we can help students develop their mathematical reasoning, that can be really helpful in this journey. So today in this session, I'm going to talk about developing mathematical reasoning. Before I do that, I want to give everybody an experience. That's an experience. It's not all the experiences, but an experience in what I would consider mathematizing, this idea of doing what mathematicians do. So I'm going to do it at kind of an interesting level. I'm assuming, because this is a TI webinar, that I have a lot of secondary educators on here. So bear with me for a second. I'm going to give us all an experience here that might be a little bit lower than your grade level, but bear with me because I think I'll be able to connect it in later to your students' experience. So let's experience a little bit of mathematizing. Am I correct that if I were to ask you right now if your students know their multiplication facts, then you would answer, of course they do. They have them down cold, right? Like they've got all their multiplication facts just like at their fingertips. Or do they? I'm actually assuming that the answer to that is that they don't really, that you have a lot of students who don't know their multiplication facts. And it kind of is a trend these days that we see fewer and fewer students knowing their multiplication facts. So I wonder if you could say to your students, hey guys, I recognize that there's some facts out there that you guys don't know. Let's maybe help each other a little bit. So could you say to them, 8 times 7? Like let's just admit right now that a lot of you guys don't know 8 times 7. Just a fact might be interesting to you to know that when researchers look at the multiplication facts, 8 times 7 is a most missed fact. It's one that kids are going to miss. So I can pretty confidently say to you that your students probably, if they're going to miss one, it might be 8 times 7. So could you say to your students, hey guys, 8 times 7, it's one that we're all missing. Does anybody in the class have a mathy multiplicative way of sort of figuring 8 times 7 so it doesn't bog you down in the work that you're doing? Is there anybody that has that? And then I might ask students, like, what do you know that could help you figure out 8 times 7? And then I might expect that a student might say something like, well, I know 7 sevens and we're looking for 8 sevens. So if I know 7 sevens, and I can represent that with a square, 7 by 7, the area is 49. So if I know that 7 times 7 is 49, how could I use that to help me find 8 sevens? Well, I just need one more group of 7. So if I have that one more group of 7, I can add 49 and 7 to get 56. And sure enough, 8 times 7 is 56. Well, that's not the only way that I could refigure 8 times 7. I might ask other students, how else are you thinking about 8 times 7? I might call on a student who says, well, I know 5 sevens. Well, okay, if you know 5 sevens, the area of 5 sevens, 5 by 7 is 35. How could that help you think about 8 sevens? Oh, well, I think I need 3 more 7s. So I could think about 3 more 7s and then add those together, and I also get 56. Can you think of any other ways? I'm actually going to pause for just a second, let y'all in the audience think for a sec. Can you think of other things that students might know that it could help them think about 8 times 7 or 7 times 8? I'm looking in the chat. We've got some interesting comments going on. I might talk a little bit about some multiplication tables or calculators or other things that students might do. Somebody said their students might say 15, 8 plus 7. Another thing that kids might say is, I know a different square. I know 8 eighths. Interestingly enough, most missed fact is 8 times 7, 7 times 8. But kids actually know 7 times 7 and 8 times 8. So if I know 8 times 8 is 64, could I take off that extra group of 8? And then what would I be left with? Sure enough, that 56. Might a kid know 8 fives? Ooh, 8 fives. How's it going to help me with 8 sevens? Well, maybe I want to think about 7 eighths. And so if I know 5 eighths, and the area of a 5 by 8 is 40, could I use that to help me find 7 eighths? And so what would I need? 2 more 8s? And that addition's even pretty slick, right? 40 and 16 is pretty easy to do. So I might ask my students, what do you know? And could you figure out 8 times 7 from there? Because I want to be really clear to send a message that 8 times 7 is figure outable. You might find it interesting. that when I wander around the country and I talk to students all around the country, I will often ask students, hey, do you know 8 times 7, or what is 8 times 7? And I find it interesting that I get two major responses when I ask 7 times 8 or 8 times 7. And one of the major responses that I get from students is they'll look at me and they'll say, I don't know. Like their response is, oh, you want to know what 8 times 7 is? I don't know what it is. As if 8 times 7 is know or not knowable. As if 8 times 7 is not figure outable. Well, it's absolutely figure outable. So I absolutely want to send this strong message to students that 8 times 7 is figure outable. And if you know these things, and I didn't just do them all, I did a few of them, but if you know these things, one of these things, then you could figure 8 times 7. So I want to send that message, but maybe by having students sort of share a little bit about how they might refigure 8 times 7. But then I'm going to get even cooler. Let's continue to mathematize. Could I say to students, hey, here's the next problem in the string of problems we're going to do today. So 8 times 7 was the first one. The next problem I'm going to give you is 80 times 7. Go ahead and solve it any way you want. I'm not going to wait very long on that. Students know this times 10 thing often, and so I'll just have everybody core response back. Sure enough, that's just 560. Cool. Well, let's see. Let me give myself a little bit of room there to deal. So the next problem in our string is 79 times 7. Go ahead and figure that any way you want. I'll give students time to think and reason about that. And then I might look around. I'll wait for students to signal me that they're ready. And then I might ask somebody, how are you thinking about 79 sevens? Did anybody use 80 sevens to help you think about 79 sevens? Now, not everybody in the room did. At this point, I'm actually expecting several students to just slam out the traditional algorithm. Might have students thinking about 77s and 97s. But I'm going to ask specifically the question, did anybody think about 80 sevens to help you reason about 79 sevens? And I would expect a student to say, well, yeah, if I've got 80 sevens, it's 560, then 79 sevens is just one less 7. So 560 minus 7, is that 553? And then I might have somebody repeat that thinking, or I might just go, well, that seems interesting, that I could kind of use something I know, 80 sevens, to help me find 79 sevens. Hey, let's just admit, guys, I'm noticing that you're also struggling with a most missed facts, 6 times 7. So then could you, as a teacher, could you also have students share 2 or 3 or 4 different ways of thinking about 6 times 7? That kind of puts the onus a little bit on the teacher. The teacher has to be able to think of what are the major strategies, the major relationships that I might want to encourage students to use to think about 6 times 7. And then I'm not going to actually do that today for time's sake, but maybe that could be your homework from our webinar today, is you could think to yourself, what are the major relationships I would use for 6 times 7? But then I'll get kids to say, okay, so it's 42. We might have figured it out a few ways. All right, the next problem in our string. What if I told you that, or I asked you 6 times 70? Well, again, I'm not going to wait very long on that. There's this times 10 thing going on. That's just 420. And the next problem in our string, I'm going to pause for a second. Anybody want to guess the next problem in our string? Yeah, sure enough, 6 times 69. So go ahead and solve that any way you want. I'll let students do that. I'll give them a second to think. And then I'll ask anybody, did anybody use 70 sixes to help you think about 69 sixes? And I'll get somebody that did, and they'll talk about they just needed one less 6. Well, what is 420 minus 6? Is that just 414? Well, it seems kind of helpful that we could sort of think and reason using something that we know. We know what 76s are. We can use that to help us think about 69 sixes. I'm just taking a look in the chat. My kiddos don't know how to use the distributive property. I believe you, and I think that this is one way of actually helping students make sense of the distributive property. Now, at this point, I can do a couple of different things. One of the shticks that I do sometimes is I might say to my students, hey, first period, I wrote this problem string on the way to work today, and I just didn't finish it. Would you guys, if you'll help me finish it, then I'll look really cool in front of second period. And so I'll just say, you'll notice that I gave you kind of a helper problem and a helper problem to do that clunker. So I gave you 8 times 7 and 80 times 7 to kind of help you do 79 times 7. And I gave you a helper problem and a helper problem to do that clunker. And I wrote the clunker, but I just didn't write the helper problem. So if I were to tell you that the clunker is 8 times 49, then could you write helper problems to stay in sort of the same vein that we just did? If we were kind of following the same pattern of the helpers that we just kind of did, well, could you write some helper problems? And then I might have students turn to a partner and talk to each other about what 2 helper problems they could come up with so that they could find 8 times 49. So I'll give everybody a chance to think about that a little bit. You're welcome to throw a helper problem or two in the chat. And we've got a couple people putting some problems in there. Sure enough, could we talk about 8 times 5 to help us think about 8 times 50? And if I have 50 eighths, could that help me think about only 49 eighths? Could I just get one less 8? And is 400 minus 8, is it just 392? Absolutely. And I would have students share that helper problem. Now, there's 2 helper problems. Honestly, I might expect that I would have some different helper problems also come out in the conversation that didn't actually follow the pattern, and I would be totally okay with that, that students found different ones. For example, students might use 8 times 40 and 8 times 9, or students might think about 8 times 100 to get 8 times 50 to then do 8 times 49. And I would be totally okay with the students coming up with those alternative ones. I probably wouldn't have them share them because typically during a problem string where I'm trying to develop mathematical reasoning, I typically just have students share the strategy that I'm sort of going for that day, but I honor student thinking because I allow them to solve the problem any way they want to. Let me ask you a question. If you would have met me today before this webinar and I would have said, hey, real quick, 8 times 49, can you figure that out? If your strategy would have been different than what we just did, if it would not have been 8 times 5, 8 times 50, 8 times 49, if it would have been something different, I would suggest that we just mathematized. That you just used relationships and connections you own to solve problems, and in the process created a strategy. You created a strategy where you could find a problem that you know that's a little too big and just take off a little extra to get the problem that you're looking for. We call this the over strategy. If you've never thought about 8 times 49 the way that we just did, then I would suggest that you just mathematized, that you literally were doing real math. And I'm going to boldly suggest that we can teach all math this way, that we can teach everything that we need kids to know by engaging them in the work of a mathematician. And as they solve problems, they can find patterns and they can use what they know to create new math for them, for the learner in their head. Now, maybe this example didn't hit home exactly for you. Let me see if we can share some other examples today of what it means to develop mathematical reasoning. So this is a graphic that I've just created to send a lot of messages. There's a lot embedded in this graphic that you can't see. And so today I'd like to talk about how we could develop mathematical reasoning in students, not just mathematical mimicry. I would suggest that when I was a student, my teachers often said, show me your work. We hear that all the time, right? Teachers will look at students and say, show me your work. But I would suggest that instead of actually meaning show me your work, we have actually traditionally meant show me my work. That my teachers said to me, show me your work, which really meant I have given you the rule, I have shown you the steps, we have done 3 worked examples. Now you should be able to mimic, do the work, the steps that I've done, and if you will do that on your paper and show me all of my steps, then I will give you partial credit if you didn't get everything right. Right? It didn't really mean show me your work. It really meant show me the teacher's work, like sort of mimic. Instead of mimicking, I want kids to actually develop mathematical reasoning. And this is interesting in the world of technology. You might find it interesting that I'm kind of advocating mental math in a TI webinar. Well, I think I'm a little bit of a unique person because I am a T³ instructor. I do believe in using the power of visualization, the power of technology to teach mathematics, but I believe in using those tools appropriately. And I believe that we can also do a whole lot of mental mathematical reasoning. So let's continue to talk about this graphic here. You might notice that we sort of build from counting strategies to additive thinking, and then additive thinking to multiplicative reasoning. And then we build from multiplicative reasoning to proportional reasoning. And then we build from proportional reasoning to functional reasoning. And notice, though, that they all are embedded within each other. It's not that once we start reasoning functionally, we don't ever reason proportionally anymore. No, we continue to reason proportionally because it's embedded within. And we don't give up additive thinking just because we're thinking multiplicatively. No, additive thinking is embedded within multiplicative reasoning. So we don't give up these less sophisticated ways of thinking. They're embedded within. We build on them to be able to think and reason more sophisticatedly. And why do I need students to reason proportionally? Because they won't be able to really reason functionally if they're not reasoning proportionally. And why do I need students to reason multiplicatively? Because they won't be able to reason proportionally if they're not reasoning multiplicatively. And why do I need students to reason additively? Because they won't be, and I know I'm repeating myself, but they won't be able to reason multiplicatively if they're not thinking and reasoning additively. And then you might notice along the bottom of this, and the kids need to be able to count as well. Then notice along the bottom of the graphic that I believe that if we do a good job of representing student thinking, of representing the relationships that students are using, that we also build spatial reasoning. If we use these visual representations, and there's only really a specific few models. I think sometimes we think that there's a lot of models modeling out there, and I think there's actually a few just really specific, powerful models that we can use to represent the relationships that are happening, the thinking. Then we can build spatial reasoning if we can make thinking visible and then expect students and ask students to reason using those models. Then we build spatial reasoning the whole way along. And also, if we actually bring the relationships to light, for example, in the experience that we just had, where we thought about, now I don't have the numbers in front of me, 59 eighths based on 60 eighths, if that was even the problem, that we can sort of use that over strategy. As was noted in the chat, we're developing the distributive property. I think we can develop the distributive property with number and work that into using the distributive property with variables. And if we do that, if we pull out that reasoning, we're developing algebraic reasoning the whole way along as we're developing all of these other domains of thinking and reasoning. So there are a few other major sort of messages that are embedded within this graphic that I'd like to talk about now. One of them is that if it's my job, if it's my gig, whatever grade level I'm teaching, to develop one of these levels of reasoning, then what I don't want to do is allow students, or even especially not encourage students, to get answers to these kinds of problems using reasoning in the level before. What do I mean by that? Let's say that I'm a 3rd, 4th, or 5th grade teacher, and my job is to really teach multiplicative reasoning. Even a 6th grade teacher, my job is to teach multiplicative reasoning. Then what I don't want to do is encourage students to use additive thinking to get answers to multiplication problems. Instead, I want to actually build their brain to be thinking and reasoning multiplicatively. If I'm a middle school teacher and my gig, my job, my task is to teach students to think and reason proportionally, then what I don't want to do is allow students, or especially I don't want to encourage students, to get answers to proportional reasoning questions using multiplicative reasoning or additive reasoning. Instead, I want them to build their brains so they're thinking and reasoning proportionally. In other words, it's not enough to get answers to these kinds of questions. I need to be building brains. I need to be building relationships and connections in students so that they're actually thinking and reasoning at these levels, not just getting answers to these kinds of questions. So to parse this out a little bit more, I'm going to throw out to you, what if, when I give this presentation live, I usually say, what if the next time you see your students, like Monday, in class? I don't know if you're like me, but my classes have been postponed for a little while. We're meeting virtually and doing all sorts of interesting things because of the pandemic of the coronavirus. So in the moment, the next time that you're going to see your students, I wonder what would happen if you ask them a question like 48 plus 5. If you said to them, hey guys, real quick, now I would suggest that you ask them in such a way that they think you actually need to know, that you're not just asking, excuse me, take a deep breath. You're not just asking them a math question, you actually need to know. So like maybe fuss around at your desk or something, or like kind of be thumbing through some papers, and then kind of look up at your students and say, hey, real quick, what's 48 plus 5? And then watch, like really look at what they do. Because your job then is to see what kind of reasoning are they using. Do they go, oh, he needs to know, she needs to know. Oh, okay, no problem. I'm going to think about, let's see, 48, 49, 50, 51, 52, 53. Do they count by ones? Now, you might not see them put their fingers up and count by ones. They've learned that fingers are evil, even though I don't think they are. They might have done it in their hair, like count by ones in their hair. They might do it under their desk. They might sort of hide how they're doing it. Kind of watch their lips. Often you'll sort of be able to tell if they're counting by ones. You guys, this is important. If we teach middle and high school, in fact, if we teach over second grade, we don't really want students thinking about 48 plus 5 using counting strategies. Remember, counting strategies was that lowest sort of embedded level of thinking and reasoning. We need kids to use counting strategies when they're in kindergarten and first grade, but we don't really want them using counting strategies past about the middle of first grade. Really, we want them thinking and reasoning additively. So what would it look like to think about 48 plus 5 additively? I'm going to give you just a second for thinking. Could I start with the number 48, and instead of counting by ones, could I think about getting to that next friendly number? Well, what's friendly? 50. Yeah, it's not about adding 2. It's about getting to the 50. And now that I've got to that friendly 50, what's left over? Could I think about the leftover 3, and then bam, what is 50 and 3? That's like my favorite question, when the question is the answer. What is 50 and 3? It's 53. That's an example of additive thinking, where students are actually thinking and reasoning in bigger jumps of numbers than 1. So I know some of you are like, really, we're going to talk about counting strategies? I teach middle school. I teach high school. Well, if your students are thinking about a problem like 48 plus 5 using counting strategies, I would submit it would behoove us all. It would be to our benefit to do a little bit of work with our students to help them to think and reason additively, so that then they could think and reason multiplicatively and then proportionally. And then if we're in the middle school, then good, we're building them as proportional reasoners. Or if we're in the high school, then we're building them as being able to think and reason about functions. Oh, I totally forgot. Bam, this is me on a webinar. I wonder, I don't really want to back up here because it'll take me a minute to, I'm going to do it anyway. Give me just a second. So if I just pop back to the development of mathematical reasoning, when I say functional reasoning, I kind of put that because I only have a little bit of space there, and I kind of want to give the right impression. But I actually don't just mean reasoning about functions. I don't just mean the vertical line test and f of x. I really mean reasoning about functions and relations, really anything that has two variables where they're both varying together. So I could put on this graphic, I could put bivariate covariation, which is what I really mean, but I think that would be a little bit funky and I'm not sure everybody would follow me. So I just kind of stick up there that it's functional reasoning, but I do really mean sort of reasoning about all of the relations that we study at the high school level. So let me pop back to where we just were, where we were thinking about 48 plus 5, hopefully not just using counting strategies, but also as using additive reasoning. And I've got to click here. There we go. So I want to be able to think additively about that problem. Well, if I may, just note that in a traditional education, what we tend to do with students at this point is say, now that you can add those smaller numbers together, whether they were counting or adding, we kind of ignore that. Then we say to them, let's add some bigger numbers. So let me give you a couple sort of gnarly numbers. These are not delightful numbers, 48 plus 99. And then we tell kids, now it is your time to learn to add. So we're going to add these numbers together. And in order to add them, don't think about 48 and 99 like you're tempted to do, because all students are tempted to think about big numbers, right? That's kind of what we do. No, instead, I'm going to teach you the algorithm. And so just focus on this column of digits over here. Just focus on the small numbers. Now, I'm going to suggest that that's counterintuitive to most learners, because most learners, when they think about 48 and 99, unless we have forced the algorithm on them, they're not thinking about the 8 and the 9. They're thinking about 40 and 90. They're thinking about the bigger numbers. Let me prove that to you. Be in your checkbook. If you were in your online checking account and you needed to make sure that you had enough money to pay your bills, are you looking at the cents, the small numbers, or are you looking at the big numbers? See, we look at the big numbers. We are inclined to think about the big numbers, but the traditional algorithm sort of forces us to do something counterintuitive, which is to only think about the small numbers. Could you agree with me that if a student is doing the steps of the algorithm, that they might say to themselves, okay, I'm going to do what my teacher told me to do. I'm going to do this 8 plus 9 thing. 8, 9, 10, 11, 12, 13, 14, 15. Could they get the correct answer of 17, put the 7 down there, put the 1 up there, but actually have been using counting strategies? And then they go over to the other column and they might go 9, 10, 11, 12, 13, and they count by ones again, and they might get that answer correct. And we say to them, yay, look, you're an additive thinker because you got the answer correct. When in reality, they were using maybe counting strategies the whole time. That's not a good thing. If it's my job to be teaching additive reasoning, then I need to be teaching kids additive reasoning, not using counting strategies. Now, you might say to me, Pam, when I use the algorithm, or when my students use the algorithm, they don't count by ones to do 8 plus 9. They might think about 8 plus 9 as 8 plus 8, and so 8 plus 9 is one more, or they might think about it as 9 plus 9, and so they might think about it as one less, or they might think about it as 8 plus 10, and they might then think 8 plus 9 is one less than that. Those are all those ways that I just thought about 8 plus 9, those are all additive reasoning. However, notice that it's only additive reasoning by single digits. The biggest numbers that I'll ever think about additively, at best, if I'm using the traditional algorithm, is columns of single digits. I'll never ever think about 48 plus 99. So it's not good enough for students to think additively, but only with single digits. Those are not the optimal case. I need students thinking and reasoning about 48 plus 99. So let me see if I can draw on some prior knowledge. And I'm noticing that Catherine put in the chat a fine way of thinking additively about 48 plus 99. But interestingly enough, the strategy that Catherine uses, 40 plus 90, 8 plus 9, and then pull those all back together, we call that splitting by place value. That keeps the place value alive. That's the least sophisticated strategy that kids can develop. And interestingly, they can develop it on their own. That's fabulous. Then we want to nudge kids towards more sophisticated strategies. Like, for example, can we think about 99? When I say that, when I go 99, don't you sort of, I can almost hear you say back to me, 100, right? 99, 100. So if I'm thinking about 99, 100, well, then I could ask myself, if I've already added 1, I'm supposed to add 48. What do I have left to add? I've got 47 left to add. Well, what is 147? Well, sure enough, that's fun, right? That's where the question is the answer. What is 147? You don't care, but it's fun. It's fun when you get there. It's a fun place to be because it usually signifies that you are thinking and reasoning and using relationships if you get to a place where the question is the answer. This is an example of additive thinking, of reasoning in terms of bigger jumps of numbers instead of just jumps of one at a time. This is the kind of work that I think we need to help students develop so that they are thinking and reasoning additively. This is where we need kids around the middle of first grade, second grade, third grade really should be working. And I know I have a lot of probably middle school and high school teachers on, so bear with me. We're gonna work up there. I have written some problem strings and some tasks and some activities to help students at middle and high school level learn to think and reason additively in such a way that it's not like going back and making them feel like they're first grade and second graders, but actually doing work with them, and I write problem strings for students to do to think and reason additively, even for middle and high school students, because we need to be able to think and reason additively in order to think and reason multiplicatively. So let's take a look at what does it mean to think and reason multiplicatively. Well, here's a most missed problem we talked about before, right? 7 times 8. If students are thinking about 7 times 8 with like a rhyme, I'm calling that fake math. I don't want to do that. That's a disconnected set of facts to memorize. If I'm doing something that's going to help me retrieve from rote memory, that's not what I want. What I really want are ways to help think and reason about 7 times 8 where I am reasoning about them. Let me actually back that up. Do I want students to know 7 times 8? Absolutely. But I want them to more than just know it. I want them to have relationships and connections that they can use to solve bigger problems, like we did before, where we did 78s and 69/8s, all based on 7/8. So I don't want rhymes. That's fake math. What does it look like if I say to myself, well, I'm going to have 8 groups, 7 groups of 8 things. So could I count out 8 things, and then I could have 7 groups of those 8 things? That's a counting strategy. If you ever see a kid solve 7 times 8 like that, maybe where they sort of deal out all of the, so whatever 7 groups of 8 things, whatever they are, that's a counting strategy. We obviously don't want students solving multiplication problems using counting strategies. We can do that in younger grades, but as they get to 3rd, 4th, 5th, 6th grade, where they're supposed to be developing multiplicative reasoning, then we don't want them using counting strategies. Well, what do we see? I told you that when I wander around the country and I ask kids 7 times 8 or 8 times 7, that I typically get 2 responses from students. One of them is they say to me, I don't know, as if it's no or not knowable. They don't believe that 7 times 8 is figure-outable. So we need to work on that. We need to help students make sure they know that it's figure-outable. But then, do you know what the second response is that I see so often from middle school students? So often. I tend to see middle school students say, I need 7/8. Okay, 8, 16, 24. And they literally start skip counting. Skip counting is additive reasoning. Now, I know we call it skip counting, so it might sound like a counting strategy, but counting strategy is where you're counting by ones. Additive thinking, skip counting, is where you're counting by one group at a time. Counting by one group at a time, that's not multiplicative reasoning either. We need kids thinking in terms of bigger than one group at a time. One group at a time is too much additive reasoning. If I'm supposed to be teaching kids to think and reason multiplicatively, who's that job? Third, fourth, fifth, sixth grade. You're supposed to be helping students reason multiplicatively, and we don't want to leave kids thinking and reasoning and skip counting. That's additive thinking. So what does it look like to think and reason about 7 times 8 multiplicatively? Well, we kind of already did that. We did 8 times 7. Let's do 7 times 8. Can I use that square 7 times 7 and just tack on one more group of 7? Yeah, sure enough, there's a way. And then here's some other ways that we could think. Before I had ways of thinking about 8 times 7. These are ways of thinking about 7 times 8. The same sort of strategies. I just have tweaked the arrays, so now they're in the same order as the number of rows by the number of columns. But that experience that we had when I wanted you to experience mathematizing, I would suggest that that is multiplicative reasoning, that we've already had an experience today in multiplicative reasoning, thinking and reasoning in terms of bigger chunks than one group at a time. All right, so we've talked about multiplicative reasoning with small numbers. What about big numbers? Then we typically, in traditional education, give kids bigger numbers, and we say to them, all right, and now here's how you can solve bigger number problems. This is what you do. And we sort of say to them, only focus on the single digits again, not thinking about 4899. Here's another moment where we teach kids math is counterintuitive. Don't think about what you're doing, just follow this procedure. Could you agree with me that if kids are going to do the traditional algorithm, that they could say to themselves, I need 8 nines, 9, 18, 27, blah, 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 and they could go all the way up, and they could find out that it's 72, and they could put the 2 down there, and they could put the 7 up there. And then they could say to themselves, now I'm supposed to focus on these other numbers over here, and so now I need 9 fours. And then they could skip count 9 fours. Interestingly enough, if they had just noticed that they were going to do 8 nines and then 4 nines, once they'd done 8 nines, they would have already found the 4 nines. But kids aren't thinking. They're just performing a series of steps, and so they keep doing the steps. Could you agree with me that they could do that by skip counting and get those correct, and then they could do the magic 0 or whatever you call the magic 0, and then they could do all the rest of the stuff, and they could keep going. But as they do, and they focus on sort of all these steps in the traditional algorithm, could you agree with me that as they're doing it, we got a little delay here. Let me wait for just a second before it catches up. That as they're doing all those different steps, and I just put X's because we're not going to put all the numbers and focus on all that kind of stuff, we might say to them, yay, you're getting correct answers to multiplication problems. You're thinking and reasoning multiplicatively. When in reality, they were using additive reasoning the whole time. They were skip counting the whole time. We can't have that because, you might be saying, but Pam, they're getting correct answers to multiplication problems. Yeah, but they're thinking and reasoning additively. Why is it so important to teach them to think and reason multiplicatively? Because then they won't be able to think and reason proportionally and functionally. Then we get kids at the middle school and high school level aren't thinking at all because they're just performing a bunch of steps. Now you might say to me, Pam, when my kids are doing the traditional algorithm, when they think about 8 times 9, they might be thinking like you did before, like in bigger chunks of numbers. They might be thinking about 8 times 8, and so they just need one more group. Or they might be thinking about 10 8s, and so they just need one less group. But even if they do that, you have to admit with me that they might be thinking multiplicative, but they'll only ever think multiplicatively about single digits. They'll never be able to think and reason about bigger numbers. We need students to be able to think about 48 times 99, the big numbers, like really think and reason about that. Now you might, if you're like me, when I was in my early days of numeracy, teaching high school math and had no numeracy, I was diving into the research that's out there about how we can think and reason. I was developing my own numeracy. I didn't know how I could think about 48 times 99. Can we? How could we think about 99 48s? I'm trying to ping on some prior knowledge that I know you have. Could you think about 99 48s as thinking about 100 48s? Oh, well, that's not too bad, right? What is 148? Is that just 4,800? But now we have 148, but I only need 99 48s. I just need one less 48? Well, what is 4,800 or 4,800 minus 48? Now, interestingly enough, kids sometimes get stuck in the subtraction. So I do a whole lot of work. If you're interested, you can check out my work on subtraction, where kids can actually think and reason about 4,800 minus 48. One of the routines that we have out there can help students do the subtraction across zeros because we help students learn their partners of 100. We call it I have, you need. I have, you need is a routine that I've got out there. If that interests you, you can sort of Google Pam Harris, I have, you need. There's a whole web blog and video out there that can help you think about how to be able to reason about 4,800 minus 48. But if you can do that subtraction, and is 4,800 minus 48, is that just 4,752? And bam, we have just been using multiplicative reasoning to think about big numbers. Okay, so we've got some examples here about having, being able to think and reason not just about small numbers multiplicatively, but also about big numbers multiplicatively. And we need that kind of multiplicative reasoning happening in students. Again, why? You might be like, Pam, really? I don't care about that. I teach middle and high school. Yeah, but if you're going to teach kids to think and reason proportionally, guess what? It is impossible for students to think and reason proportionally if they are not thinking and reasoning multiplicatively. Oh yeah, students can get answers to proportions. They can solve proportions, but they're not building their brains, building the relationships in their heads to be able to reason proportionally. Well, what does it mean to reason proportionally? Let's take a look at that for a minute. So you might find it interesting that 90% of adults do not reason proportionally. 90% of adults do not reason proportionally. That's a huge number. That says to us that there must be some active help, that people are not going to learn to think and reason proportionally on their own. We have to actively help them. When I was developing my own numeracy, my own reasoning ability, I was really starting to mathematize. I picked up a book called Teaching Fractions and Ratios for Understanding by Susan Lamont. She's the one that says 90% of adults don't reason proportionally. In her book, she says, do you reason proportionally? I said, of course I do. I'm a high school math teacher. I am the god of math. Of course I reason proportionally. She said, if you reason proportionally, here are 10 problems. You should be able to think and reason through these 10 problems. Not set up a proportion across multiply and divide. You have to actually think and reason through them. And if you can, then you are reasoning proportionally. I said, this no problem. I am a high school math teacher. I am the god of math. Of course, I can reason proportionally. So I read the first problem. I skipped the first problem. I read the second problem. I skipped the second problem. You guys, I had no access to those 10 problems. I could not reason through them. Now, I could set up a proportion across multiply and divide for about half of them, but I could not think and reason proportionally. And for the other 5, I had no access. I couldn't even, there was a couple of them where I could kind of remember there was a formula that I hadn't seen for a while, but I couldn't remember what it was. My point here is to say the thinking and reasoning proportionally needs to be developed. And I, as a high school math teacher, was not thinking and reasoning proportionally. So I'm actually not going to do a whole lot of work on proportional reasoning in this webinar today because probably 90% of us aren't thinking and reasoning proportionally. May I recommend that I've got a lot of work out there. I'll give you some resources at the end of the webinar where you can start to build all of these kinds of reasonings. And maybe you already do think and reason in all of these ways, and that's super. I'm so glad. I also, in my work, can help your students build their reasoning. So I'd like to actually now think about what we typically do at the middle school level to solve proportions. To solve proportions at the middle school level, what do we typically do? We typically teach kids to cross multiply and divide. Guys, where do multiply and divide live in the development of mathematical reasoning? Yeah, that's in the level before. Remember what I said earlier? The imperative is that if it's our gig to teach kids to think and reason in these ways, what we don't want to do is allow them, or especially we don't want to encourage them to use reasoning in the level before. We want to actually build their reasoning. Somebody just said guilty. Totally, me too. Like, I get it. But now that we know better, we could do better, right? And so, again, I'll give you some resources on helping you and your students build these levels of reasoning. So what we don't want to do is help kids get answers to proportional reasoning problems using reasoning in the level before. That's why I don't advocate cross multiply and divide. There are other ways to solve proportional reasoning problems that build proportional reasoning at the same time. Okay, we're going to end the webinar talking about functional reasoning. So what does it mean to think and reason about functions? Now, typically if I was doing this presentation live, I might do the string that we're about to do, the problem string we're about to do, but I typically like to do a couple of other ones. But in order to make it work with this kind of strange virtual, we're going to do this one. So hopefully it will work well. Bear with me, be patient with me a little bit. Could I say to students, hey guys, real quick, the first problem of the string today is let's go ahead and graph x squared. Now, don't put it in your calculator. I'm using the calculator interface because as the teacher, in this problem string, I would be using technology to graph these guys quickly. I would sketch some things, and other things I would use technology. But I would have my students at this point be non-technology. So I would say to them, hey, just really quickly sketch x squared. And when you do, give me some important points. So I would give students a chance to do that. I would expect students would come up with a graph that looks something similar to this. And then I would say to them, what are some important points that we might put on that? And they would suggest some important points like this. So I would sketch these on the board really quick. I might do it with technology. I might just sketch either way. Get close enough that I've got something that's fairly close to y equals x squared. Okay, so the first problem is not going to take us very long. It's not hard. We would have had to have done work before kids. I'm assuming at this point kids have some experience with quadratics. Then I might say to students, okay, next problem of the string. The next problem in the string is I'd like you to graph on the same axes. I'd like you to graph the line y equals 3x. And I might not even tell them it's a line. I might just say graph y equals 3x. And then I would expect students to graph that. I would give them some time to graph that. And then I would think about, I would give them time to do that. And I would look around at what students have. And then we would go ahead and sketch that on the board. And I would ask them also for some important points. And we would put those important points up. So I'm kind of whipping through parts here that I would take a little bit more time to actually do with students. Hey, I'm just noticing a question in the chat that I'm going to actually go ahead and answer. Somebody said, what about using 40 plus 8 times 90 plus 9 and then use double distribution? So that's, and I just call that distribution. I think it's a little bit funky to put specific, anyway, we're just going to distribute. Do we absolutely want to have kids be able to do 48 times 99 as 40 plus 8, that quantity times the quantity 90 plus 9 and use the distributive property? Absolutely. But again, that's actually the least sophisticated way we want kids to do it. That's like the beginning strategy. Eventually, I want kids to be able to think about 99 times 48 as 99 48ths. I need kids to be more efficient than always using all of the chunks. So all of the chunks is the place we start with kids, and then we want to get them to a place where they can think more efficiently and more sophisticatedly about multiplication. And then absolutely using the rectangle model, area model is a good way to visually represent that thinking. Okay, so in this problem string, the first problem, again, x squared with some points, then 3x with some points, and then I might say to students, okay, cool, right, you ready for the next problem? So the next problem of our string is, now I'd like you to think about, what would this graph look like? X squared plus 3x. X squared plus 3x. What would that look like? And then I'm going to let students go. I'm going to wander around, I'm going to circulate, I'm going to see what students are doing, and then I'm going to choose some students to share. So I'm going to give you guys a minute to think about, what do you think the graph of x squared plus 3x looks like and why? So thinking. And I'm going to go look for students who specifically are wondering to themselves, what does it look like to add a function to a function? We've already got x squared up there. We've already got 3x up there. And now you want me to add them together? Weird. So let's see how this works. I don't know if you can see that blue thing, so I'm going to kind of move it a little bit and then put it back. But that represents the height of the blue function, the quadratic, at 1. And then this red thing is going to represent the height of the line at 1. And so if I take those two heights and we sort of add them together, because, right, we're adding the two functions together, we're adding the y values together, then the height of the new function should be up there at 4. And so we'll go ahead and put a point there at 4. Okay, so we think the new function we're going to graph in black, that's going to be up there at 4. And then I might say, what about at 0? Well, both the quadratic and the line at 0 are the y value of 0. So if we add 0 and 0, then we get 0. So there's another point on our thing. And then we might look back at -1. At -1, I'm still up 1, but the line is down 3. So what happens when we have down 3 and up 1? Well, that's just going to be up 2. So let's go ahead and we'll put that, or excuse me, down 2. So that's going to be at -1, the new function is going to be down at -2. So we'll go ahead and put a point there. Do you see what we're doing? We're sort of taking y values of both of the functions, and we're adding them together at certain x values, and then we're getting points on our new function. Well, that's interesting. Okay. Well, I wonder what's going to happen let's keep going to the left. What about at -2? What's going to happen? So there are the values at -2, and if we sort of add those guys together, we're a little bit more negative, and so that little bit more negative space will kind of stick where it belongs. Whoa, that's interesting. That's going to be a point at the same place. Huh. What are you thinking about that? Maybe we'll keep going. We'll sort of ask ourselves what's going to happen next. What about at -3? What's happening at -3? Well, -3, interestingly enough, both the parabola and the line are both 9. One of them is positive, one of them is negative. 9 plus negative 9, that's 0. Well, that's interesting. Now we're back at 0. Oh, we're starting to see a pattern maybe appear. Okay. Okay, it looks like we might have a quadratic happening. Now, this is really hard for me, and I didn't figure out a way to do this. I would ask you to think a little bit, and I would spend time here talking about what's going to happen to the right of 1. So everybody look to the right of 1. And I can't even point or anything. So just look to the right of 1. To the right of 1, I have both the line and the quadratic being positive. So what's going to happen when I add positive values to positive values? That sucker's going to just be positive. What happens to the left of negative 3? Again, I really wish I was pointing and touching things on the graph and stuff here, but to the left of negative 3, I have the quadratic being positive, and I have the line being negative. And then we would want to talk about who wins, the quadratic or the line, as we sort of add those y values together. And then we might go ahead and graph, like sort of connect those dots. And, well, sure enough, we've got this sort of quadratic going on over here. So a quadratic plus a line is another quadratic. And I would want to talk about the end behaviors and why that's kind of true. Okay, that's interesting. Now, I would also be looking for a different strategy to graph this. And I would be walking around and I'd be looking for a different strategy. If I didn't see it, then it would become the next problem of the string. And so the next problem of the string could be, hey guys, what is x times the quantity x plus 3? See how this could have been a strategy that somebody could have used to graph y3, to graph our x squared plus 3x? Because what jumps out at you? Oh, bam, the zeros jump out at you. And notice on our graph, we actually have those two zeros at negative 3 and at 0. And that could have told us right there, we've got a quadratic with those two zeros. That could have been a great strategy to graph. Interesting, 2 different strategies. All right, that's really kind of cool. What's the next problem in our string? Are you ready? You're excited, I know you are. The next problem in our string is, sorry, before I did that one, so that I went ahead and graphed x times the quantity x plus 3 so that we could see that it is indeed the same function. So now we have the black and the pink are the same function. All right, the next problem in our string. What if I asked you to graph x squared minus 3x? What does that look like? And I'm not going to spend the time here in the webinar, but I would let kids mess around with it, and they would think, and somebody in the room is going to notice that blue quadratic kind of looks like it sort of shifted to the left and down to become the pink one. And they're going to wonder if it could shift the other direction. They're going to wonder if in what reality actually just the new function shifts the other way. And we can support that by looking at the factored form of the equation. So I don't know what you think about this little task, but I would suggest that this is an experience of thinking and reasoning functionally. It's not about rote memorizing stuff. It's actually about thinking and reasoning and helping students really understand what's happening. And then the last problem of the string I could give students would be, I wonder if you could think of a way to graph x squared plus 3x plus 5, something that's not factorable, as in like undistributing FOIL, something that's not factorable that way. Could you just sort of factor an x out and get x times the quantity x plus 3, graph that, and then shift it all up 5. Bam! And I wonder if anybody on the webinar today just developed a brand new strategy for graphing a quadratic that's not easily factorable. We can hope. All right, so I've just given you an example of thinking and reasoning functionally in the development of mathematical reasoning. I hope you have some sense of some of the points I'm trying to make. We didn't talk about all of them, but the huge idea that if I'm supposed to be teaching this kind of reasoning, what I don't want to do is encourage kids to use reasoning from the levels before. I want to encourage them to actually think and reason about the thing that I want to build their brains to think and reason relationally. So in my new book, If Not Algorithms, Then What? I'm going to talk all about the development of mathematical reasoning. I've got lots more examples. I'm still writing it, so I'll let you know when that comes out. I'm not going to have time to do this. Sorry, Fildaro. I do want to tell you that at my website, if you're interested to follow my work, on the homepage, it looks slightly differently than this now, but you can submit your first name and email, and totally free. I just send you weekly emails, and you can learn more about the development of mathematical reasoning and a lot of other things. So I do a lot of things. I'm not a one-trick pony, and I've got lots of different irons in the fire. So if you teach K-12, you might be interested, if you're a high school algebra teacher, you might be interested in my algebra problem strings, my advanced algebra problem strings, lots of different work going on. So this would be a great way for you to follow me. This is my website, mathisfigureoutable.com, but honestly, the easiest way to find it is to just Google Pam Harris Math, and it'll come up. The other thing I'd like to invite you to do is join us totally free on social media on Wednesday nights. Math Strat Chat is awesome. I throw out a question. This is the one that we just did. Actually, it was 2 weeks ago we did this one, 129.6 divided by 10.8. And I literally asked the world, how are you thinking about this? We've done some proportional reasoning problems. I'm about to maybe do some high school problems. I'm still thinking about that. But I would love for you to join us there on Math Strat Chat. You can Twitter, Instagram, and Facebook. You can throw out your strategy, or if you want, you can just lurk and see what other people are doing. Lots of fun. I noticed some people on the webinar today actually participate on Wednesday nights, and I love chatting back and forth with you about how you think and reason. Here's some examples of some of the Math Strat Chats that we have done. This is Math Strat Chat Central. If you go to my website, we actually have are archiving them all, so you can click on any one of these and you can see strategies from people all across the world. I've written some books called Building Powerful Numeracy for middle and high school students. You might check those out if you're interested. These are my algebra problem string books. I think they are phenomenal at teaching students to think and reason about functions. I also have some online courses if you're interested. I have a feeling some of you might be a little stir crazy the next few weeks if you are not going to school with your students. So if you'd be interested in an online course, check out my website and you can learn more about those. I'm also about to put out on my website, and when I say about, that always means 6 months from now, videos of expert teachers and students in real classrooms doing problem studies like we did on the webinar today. Those are totally going to be free on my website. So again, keep track of my website if you're interested in ways to teach real math, not fake math, or really experience math, because I want to teach kids to mathematize. I want to mentor mathematicians, and I think it's all about relationships among numbers and structures to solve problems, and between teachers and students to nurture and mentor young mathematicians. I volunteer. I think that it's also about the relationship between teachers and curriculum writers, which I consider myself a curriculum writer, to nurture and mentor each other in our own personal professional learning community. So if you'd like to join my personal professional learning community, I welcome you to ping me on Twitter or Facebook. We have a teachers group on my Facebook page. Would love to have you join us there. Also, if you're interested to download a How Do You Reason document that helps you decide where your students are on the development of mathematical reasoning, you can go to this link. It'll be on this next page as well. This is my contact information where you can find me. And again, there's that link where you can download a really cool How Do You Reason, sort of help more and more about the development of mathematical reasoning. I really appreciate everybody joining in today. I am a minute early, but I don't know that we have time to do a whole lot of questions on the presentation. But thank you for joining today. If you have any questions, ping me on Twitter or in the teacher page in the Facebook page, and I'd be happy to answer any questions. Thanks again for joining today, guys.
Thank you, Pam. I know that I am so looking forward to having the chance to explore your resources, your all of the things you have listed there. Everybody, just so you know, this is recorded. You'll get email that has information about accessing the recording and documents, and it will also, your email will also have the link for your certificate of attendance. The chat panel is going to stay open for a little while, so you can touch base with Pam there. I know that there's another session coming up shortly, and people are going to have to exit one and go to the other. Thank you all so much, and thank you, Pam, for the energized, oh my gosh, how did you get it all in those 55+ minutes? Thanks, everyone.